So there are two different directions in which we are going to go in. One of them is going to be a transform and conquer approach. And the second would be an enhance and conquer approach, which is something we have done in a class on prefix sums earlier, something like that. So transform and conquer. How do we take the input and transform it in some way? The way we will transform it is not by using any kind of data structure, but something sort of the converse of what we did with in the bit manipulation classes. So in the bit manipulation classes, we said that in some problems, it helps to not look at this array of integers, the given array of integers as an array of numbers, but really as an array of bit strings. Or if you're given a number, instead of looking at it as a number, you look at it as a bit string. And so you change the lens with which you're looking at it, you transform the way you look at it, and that allows you to start using bitwise operators to solve some of these problems faster. So here also we'll do something similar. Here we have strings, we don't have integers, we have strings. And one thing we know is that this work that each manager is doing, which is taking order m time, is taking that long because these m characters are the string is made up of these m characters. But suppose these were not characters, suppose they had been numbers. In other words, the text had been a sequence of, say, digits. The pattern had been a sequence of digits making up a number. In that case, what we would do is we would have, at any stage, whatever the fixed length window we have of size m, we look at the number within that window in the text, and we look at the number that the pattern is equal to, and we would equate the two numbers. How much time does it take to compare two numbers on a typical machine? Well, that comparison can be done in constant time because that could be, say, a single assembly language operation where for example, you just subtract the numbers and check if the output is a 0. So that can be done as a single elementary operation. And if we can do that, then the work that each manager is doing would come down to order 1. And so the total amount of work needed would be order n minus m plus 1, which would be order n. So that's the idea. The idea here is to treat the substrings or the strings as numbers. Being checked for equality. So just as an example, what we'll do is we'll start out by assuming that T is a string where the characters are, say, our familiar digits. Say 2, 3, 5, 9, 0, 2, 3, 1, 4, 1, 5, 6, 7, 3, 9, 9, 2, 1. So pretty big. And let's say the pattern is 3, 1, 4, 1, 5. Now just by visual inspection, you can see that this appears here in the text. But we want to see how we can algorithmically catch that. So since we want to treat these characters as numbers, and it's pretty clear how to do that if your characters are drawn from 0 through 9. This number is 31,415. So we know how to compute the numerical value of p. So by the way, how would we compute the numerical value of p? which in general is going to be of length m, right? Because we need to compare at every stage the numerical value of p with the numerical value of the substring in t. So the numerical value of p will need to be computed explicitly, because 31415 here are assumed to be characters, not literal digits. So we need to convert this character 3 into the number 3. Then when we look at 1, we need to convert it into the number 1 or the digit 1. And then we need to combine 3 and 1 to make 31. Likewise, 314, when we look at this as the digit 4, then 3141 and 31415. So I think in a previous class, I'm not sure which one it was, one of the bit manipulation classes maybe, we looked at Horner's rule, which is a decrease and conquer way of computing the value of a polynomial in general. So let's say I know what the value of the first I characters is. So if the last digit, or let's say the next digit is a 3, so in that case, so this digit would have a place value of 10 to the power 0, this would have a place value of 10 to the power 1, 10 to the power 2, 10 to the power, say, I minus 1. Now what would be, so if we know what the value of this part of the string is, what would be the value of the entire string including the last 3? Well, we take whatever the value was up to that point and we multiply it with 10. 10 times the previous value and add the 3. Because the 3 is going to become the new digit in the ones place. And all the other digits are going to shift to the left in terms of their place value. And shifting left by 1 is equivalent to multiplying by 10. So that means this p, we can compute the numerical value in order m time. What about the numerical value of t, or really a substring of t of length m? So if we focus on, let's say, the leftmost substring of t, or any substring of t for that matter, we can compute its numerical value also in order m time. So the numerical value of p or any substring of length t, sorry, of length m in t. So the leftmost substring of t is something we would compute in order m time, and then we would check whether the numerical values of p and that substring are the same or not. If not, we will focus on the next set of m characters in t, compute its value, and do the same thing. Now this can be done in order m time, but the problem is that if we compute the value of each substring of t in order m time, then this work is still going to be order m, which will not improve our complexity. This part, the pattern of course remains the same in each step, so we can just recompute the numerical value and just keep using it. But if the numerical value of each substring of t has to be computed in order m time, then we are not saving anything. And this is where it helps to look at this as a fixed length sliding window problem, because when we move from the white window here to the yellow window, what is really happening is that the leftmost character goes out of the window and the rightmost character here enters the window. The other characters are the same. So if we can take the numerical value computed by our previous manager, and from that deduce the numerical value of our window in a constant amount of time, then this would effectively make the work being done by each manager as constant time work, and that would bring down the complexity. So can that be done? Yes, it can be done. So the numerical value of any substring of t, the next, let's say the numerical value of the next window, can be computed from the numerical value of the previous window by taking the numerical value of the previous window and discarding from it the numerical value of its leftmost digit. So what is the numerical value of the leftmost digit? So if my window was of length m, whatever digit is in the rightmost place, it would have a place value of 10 to the power 0. This would have a place value of 10 to the power 1. The leftmost digit would have a place value of 10 to the power m minus 1. So what we need to do is to take the numerical value of the entire white window computed by our manager and subtract from it the numerical value of the leftmost digit here, which is really going to be whatever that leftmost digit is, that times 10 to the power m minus 1. So that's the first step. So the next value would be whatever the previous value was. From the previous value, we subtract 10 to the power m minus 1 times the leftmost digit in that window, in that previous window. So that will give us the numerical value of these characters. Now, when we add one more digit on the right side, we have to do what we did here with Horner's rule, namely take this value, multiply it with 10. So take this whole value, multiply it with 10, and then add to that the new digit that came in from the rightmost digit of the new window. This is the leftmost, sorry. This is the leftmost digit of the old window. Or the previous window. So how much time would it take to do this computation as we move from one fixed length window to the next fixed length window? 10 to the power m minus 1 is something that it's a fixed number. So this can be computed in advance. It's not going to take more than order m time. It could be done even faster, but let's say even if we just multiply 10 by itself m minus 1 times, we can pre-compute this and store it somewhere. So that multiplied by the leftmost digit, that's a single multiplication operation. This is a single subtraction operation, again another multiplication operation. So this whole thing can be computed in constant time, and then adding a new rightmost digit can also be done in constant time. So that means the entire update, this update can be done in constant time. Constant time update of the numerical value of the next substring in T. Okay, so this change, So this change is going to bring down the complexity of the whole algorithm. And if we want to go back to the scenario where we have English letters, let's say our string is composed of the 26 characters of lowercase letters of the English alphabet. We can interpret any substring there also as a number. Instead of using a base 10 value, we'll use a base, say, 26 value, right, where the digit A corresponds to the value 0, the digit B corresponds to the value 1, the digit Z corresponds to the value 25. So whenever we see a character, we just have to convert it into its corresponding digit value. And then in this formula, wherever we have a 10, we can substitute it by 26, we can replace it by 26. And that would give us the corresponding numerical value. You might remember in the URL shortener problem, for example, how we were using a base 64 representation where not just digits but any of the characters um, in the English alphabet were included and were interpreted as the whole string was interpreted as a number. So this is going to be linear time provided we can implement this correctly. One of the problems, actually the main problem with this implementation, and this would definitely work provided the numbers that we are getting for the substring values are not too large. So if our substring is of length m, whatever the value we compute for, say, the largest possible substring of length m, that value, as long as that value fits into the, as long as it doesn't overflow, this would work. But the actual problem is going to be that m could be large enough. M could be so large that the pattern P and any substring of length m in T, one or both of them, could be too large integers to work with. Now the way to fix this would be to, if they are too large, just bring them down to within a range that's manageable. It's kind of like how you might have seen in some of the dynamic programming problems, where the answer could be so large that whenever the number becomes large enough to be in danger of overflowing, you take the mod of that number with a large prime number to bring it back down into a range that can be represented. So we'll do the same thing. We will, whenever we are doing these numerical operations, we will work with, we will do a mod operation with a large prime number q. So q would be a large prime. It should be large, but remember what we are doing here is multiplying this value with 10 or 26. So this entire, whenever we do this multiplication, that itself should be doable on the machine. So 10 times uh, q or 26 times q, for example, should also be representable in the, on the machine, so that um, so that there won't be any overflow. So q is a large prime, so, but small enough that 10 to the power q, 10 times q, or you can say 26 times q, will fit within the maximum integer value, whatever the max int value is. And in a few minutes we'll see what how large we want q to be. Turns out that it will turn out that as long as you pick q to be more than n, the length of the string, that should be good enough. Doesn't have to be super large. So what does this mean? What does it mean to use this mod q? So that means if you go back to that formula, then the numerical value of the next substring is going to be obtained from the numerical value of the previous substring by subtracting from it the leftmost digit in the old window times, I'm going to pick d to the power m minus 1. So d could be 10, it could be 26, it doesn't matter. In general, we'll be working with some, some d is some general radix, some general base. And it turns out that d to the power m minus 1 itself could be quite large. And so the nice property about um, modular arithmetic is that you can keep taking mods whenever the numbers, with every operation, and the final result is not going to change. Whether you take the mods sooner or later, that's not going to affect what the final answer is. So the sooner you take the mod, the lower the chances of there being an overflow. So you take this, you're going to multiply it with d, and then add to that the rightmost digit, and again take mod with respect to q. Now this fixes the issue of integer representation, but it introduces a new issue, which is that when you take mod q, it is possible that two different numbers, when you take mod q, could leave the same remainder after the mod operation. So this is susceptible to collisions, you can say, which are also called spurious hits. And to see how that could happen, let's go back to the example we saw. Um, so let's say our pattern P is 31415. Let's assume that, since I'm just showing this with a toy example, let's say we've picked a value of Q that is, say 13, right, quite small. And let's say our text T is 23590. So we'll start with, let's say, so our pattern is of length 5. Um, so when we take 31415 mod q, right, we won't be working with a value of 31415. We'll be working with values that are going to be in the range from 0 to 12 because we're always going to do a mod q. So 31415 mod q is equal to 7. So this value is effectively 7. This value 23590, when you take a mod with 13, turns out to be 8. The next value 35902, that turns out to be 9. Okay, the next value 59023 turns out to be 3. The next value which ends at this 1 turns out to be 11. The next value which ends at this 4 turns out to be 0. The value that ends here turns out to be 1. And then finally, well, not finally, but at this point, we are going to get 31415. And so when we take 31415 mod 13, we are going to get 7. So as we are sliding this window of length 5 here from left to right, we will be computing these mod values. And whenever we see a value matching value of the pattern, we will consider that a match. Now this will continue on, but when we come to this window 67399, it turns out that when you take mod of 13, you also get a 7. So even though the substring in T 67399 does not match the pattern, after taking a mod operation, we can get a spurious hit. Okay, just to recap, how are we taking this operation? So suppose we have 31415 already computed. Suppose we want to go from this red window to this blue window 14152. The way we will uh, compute the new value is we'll take the old value. So actually, let me just write down the formula, then I can substitute. We'll take the old value and subtract from it. So d, which is 10 here, 10 to the power m minus 1 times the leftmost digit, which is actually 3 in the old window. Uh, Without mod, we would have done this. Then we would have multiplied it with 10, and then we would have added a 2. Okay, but with mod, what we will do is we will compute 10 to the power 4 in advance. So 10 to the power 4 is going to be used in every step. So 10 to the power 4 4 does not have to be stored as 10 to the power 4. We could compute its mod with 13, which is actually 3. So in effect, in the mod q system, 10 to the power 4 is really 3. So 31415 itself, the old value was 31415 mod 13 was 7. Right. So this is 7 minus 3 times 3. And then you multiply it by 10, and then you add a 2, and then you again take a mod of the result with 13. So this is going to be again mod 13. If you do the calculation, this turns out to be 8. Okay, but if you continue on, you'll see that when you come to this window, the value you'll calculate is going to be 7. And that will lead us to a false conclusion that the pattern appears at this point in the text as well, which it doesn't. So the way to, so how do we handle these collisions? Well, whenever we see the same signature, the same fingerprint, you can say, or the same code, mod 13, we know that there is the possibility of collision. So at that point, we can make an explicit check between the actual characters to see whether the actual characters match or not. If they do, then we append it to the answer. Otherwise, we don't. If there is a mismatch, if the codes don't match, clearly the pattern and that substring of t don't match. Okay, so what does the time complexity here look like? So the total time. So the hope is that there will be few collisions. How do we ensure that there are few collisions? Well, firstly, we need to make Q as large as we can. Because if we make Q as large as we can, then the valid values after taking mod Q are between 0 to Q minus 1. And if that range is bigger, then the possibility of collisions is smaller. So make Q as large as possible so that there are as few collisions as possible. And when there is a collision, or even if we get a match, we are going to explicitly compute. We are going to explicitly compare the characters, the m characters, and then add that value, that particular shift to the result only if we confirm the match. So the total time is going to be the time needed to pre-compute all, what does the algorithm look like? First, we pre-compute, say, the numerical value of the pattern, the numerical value of the leftmost substring of t, the numerical value of d to the power m minus 1. So these are three of the values we have to pre-compute, which can be done in order m time. Pre-computation. And then we start our sliding window where in each step we can compute the numerical value of the next window from the previous window in constant time. So since there are roughly n minus m plus 1 such windows, that's the amount of time we'll take. This is the part where we have a fixed length sliding window. And then if we saw C matches, suppose there were C times that we saw a match between the text and the pattern, we might explicitly compare the characters for each of those C matches. So that would take order Cm time, right? This is, you can say, verification of those C matches. So if we can argue that the value of C is going to be small, then overall this whole problem would take linear time. Right? So if C is small, then overall this would take order n plus m time. Now, strictly speaking, it's not just how many matches there are that have to be verified, but also we need to add to this the time for processing spurious hits, because those will also tend to match, but while making an explicit comparison, we'll realize that they actually don't match. So we are going to take order m time for each spurious hit. Right? So the question is, how many spurious hits will there be? Now there are in total how many windows do we have? N minus m plus 1 windows. If we just, you know, uh, argue at a very high level that, well, each of those windows, each of those values is likely to be mapped to some random value in the range from 0 to k minus 1. Um, the the number of spurious hits that you are expected to get, right, or the number of collisions you can say you are expected to get, would be something like n minus m plus 1 divided by q, right? Because this q in the denominator is the total range. These are all the total number of different values you'll have in the across those sliding windows, and you'll be, of course, some of them will be the same, but I'm just ignoring that. When you map them to q, a range of size q, assuming that they are uniformly distributed, we'll get roughly these many values per bucket. And so if we pick the value of q to be larger than n, then this value is expected to be less than 1. So not that many collisions. You do not expect that many collisions. And so the time for processing spurious hits would also be order m. Okay, so choose q to be greater than equal to n so that this value is less than or equal to 1. Even if it's 2, it's okay. It would still be order 2m, which is order m. Uh, so that's how our algorithm would work. You can say in expected linear time. And this algorithm is known as the Rabin Karp algorithm. People usually call it as a rolling hash algorithm because essentially the numerical value you're computing, and when you treat them as digits, and then when you take mod q, you can treat those operations as basically a hash function that's being applied on the string to yield a numerical value. And as you move from one window to the next window, uh, the hash value can be updated for the new window in constant time. So that's called a roll. That type of hash function is called a rolling hash. But it's so the terminology looks a little different, but it's essentially the same fixed length sliding window problem. So I would actually call this as fixed length sliding window algorithm. So let's write the code for this. So let me take any questions if there are any before I write the code. No questions. Okay. So let's see how to write the code. So firstly, as I said, we'll assume that m is the length of the pattern. P. N is the length of the text. T. And if m and n or m or n happen to be 0, or if the pattern happens to be longer than the text, obviously there's not going to be any matches, and I'll assume that those can be handled as edge cases. Yeah, questions, Arif?
Omkar, I think your window froze. Need to reshare.
Oh, okay, sorry. I hope that's visible now.
Yeah.
Okay. Umesh?
Anchor. In the time complexity,
Hmm.
we already factored in for verification of the matches, right? Whenever the values match, at that time we are comparing the strings if they are really equal or not. Then why we are explicitly again adding for time for processing spurious hits?
Because these C matches are actual matches and the spurious hits are false matches.
Okay.
So we will, since these are the two we want to separate out by making those explicit comparisons. I'm arguing that both of them uh, can be expected to be small enough that this explicit matching phase will take no more than order m time. In fact, what you could do is you could pick q to be large enough that if you think that the possibility of collisions is really low, you don't even need to do an explicit match. So in that case, it would just be the first two components here that would suffice.
Okay. Yeah.
So in the problem that I have, this problem, you can actually implement. So in this problem, it's basically the substring matching problem. You want to you're given a text string called a haystack, and you're given a pattern string called a needle. You want to find out the first occurrence where the pattern occurs in the text. So it's an easier version of the problem that we're actually trying to solve. We're trying to get every single position where the pattern occurs. Here you're supposed to return only the first position. Uh, so if you pick a value of q that's large enough and the possibility of collisions is low, your code will actually run without your doing an explicit matching. So when you implement Rabin Karp for this problem, you'll see that even without an explicit match, it will pass all the test cases if you pick q to be large enough. Govardhan?
Oh, hi. Can you go back to the previous slide where you have written in the blue color?
Mm-hmm.
So here, let's say the pattern is 31415.
Mm.
So you're basically you're calculating the value 10 to the power of 0 times 5, 10 to the power of 1 times 1, like that, right?
Using Horner's rule.
Yeah.
Yes, but the formula is what you said, but the way we compute it is by using Horner's rule.
Okay, but the thing is here, the new value,
Mm.
you are deducting the previous value 10 to the power of m minus 1.
Mm.
Okay.
Mm.
You are simply adding it 2 followed by like there, wherever it is matching, the next number is 2.
So yeah, 2 is the new element that's entering
Yeah.
the window.
But
3
in
is
this
the old
case,
element that's leaving.
the power of 10 to the power of 3 will change. It is earlier it was, let's say in this case, 0, 1, 2, 3, 4. The power of 3 was 4. Now the power will change, right? 10 to the power.
We are also multiplying by 10, the whole parentheses.
Yeah. So when you multiply by 10, all of so 1415 is what you'll be left with. It will become 14,150.
Okay.
And so
But,
when you add the 2, it becomes
then the mod of
14,150.
13.
Yeah. So ignore the mod. Conceptually, what's happening, what the algorithm is doing is it's treating these strings as integers.
Yes.
So that you can compare them in constant time instead of order m time.
Yeah. I understood
And
that.
the mod is just a hack to avoid integer overflow.
Okay.
And that in turn introduces the possibility of collisions, and that's why we pick a q that's large so that the probability of collisions is minimized.
So that means in our algorithm, whenever there is the spurious it happens, we are again checking exact character to character.
Yeah.
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 Okay.
Kaustubh?
Yeah, hi Omkar. So I have a question about Q larger than N. So you mentioned Q should be large enough but small to fit in maybe a register of the computing machine.
Yeah.
But does that mean that if we have a really large pattern, sorry, a text, which will imply the n is a really large value, this may not work.
Yes. So, but if you look at what's actually given in interviews, sorry, I have to again reshare. So if you go to that lead code problem, uh, the length of the string is relatively small.
There will be some constraints on the
Yeah.
problem. Okay, got it. All right.
So here, for example, it's 5 times 10 to the power 4.
Got it.
So that
Okay.
means 50,000.
Yeah. Okay.
So you can easily pick a number
Sure.
that's more than 50,000, a prime number
It's a
more
prime.
than 50,000. Yeah.
Thank you.
And why do we pick a prime number? Because so when we are doing mod q, we are essentially dividing by q and getting the remainder.
Correct. Correct.
So
Yeah. Get the hash value.
if q is not a prime number, then there is a possibility that the number which we are taking a mod q with, there is a bigger possibility that uh, it could have some common factors with q. And so if there are common factors, then you can reduce the fraction. So the denominator and numerator won't be as large because there'll be some cancellation. And if there's a chance of cancellation, then you effectively the denominator would become smaller. And so that means the mod value will be then in a more constrained range rather than 0 to q minus 1. It's going to be 0 to some smaller number minus 1.
Right. Yeah, that's I think also how in Java when they implement the hash function, they make use of these prime numbers, right, to calculate the hash value. So I think it's
Yeah.
the same principle.
Yeah.
Thank you.
Okay. Arif?
Omkar, my question is, so why we are on the previous slide here. So you are counting the time for verification. Also,
Mhm.
you're counting the time for processing the spurious hits.
Mhm.
So is it not like, let's say you have 5 hits total that gives you the same remainder, and out of them, 2 of them are actual matches.
Mhm.
So your total is 5. So you could only count the spurious hits or the total hits. So are you saying that the total hits equal to the number of exact matches plus the spurious hits?
Yes. Yeah. So the total number of matches with the pattern will be actual matches, which are C in number, and spurious matches, which are, of course, we don't know how many there are, um, but the estimate is that um, since this is the probability of a collision, very loosely speaking, m times that. Uh, since this is the probability of collision, we will have these many on average per bucket. So when we do mod q, there are q buckets, right? And if there are n minus m plus 1 numbers whose mod we will be taking, making a very simplistic assumption that they will get distributed uniformly among those q buckets, each bucket will have roughly n minus m plus 1 by q uh, copies or numbers that will fall in. So that's basically what I'm approximating as the number of collisions.
Yeah, thanks.
And if q is bigger than n minus m plus 1, then uh, the expected number of elements per bucket will be less than 1. Okay, so let's write the code now for Rabin Karp. I'm going to assume a d value of 26, but could be something else. So let's assume the lowercase letters. So remember that we wanted we wanted to pre-compute this value, right? Or you can say this value d to the power m minus 1 mod q would need to be pre-computed so that we can reuse it again and again. Likewise, the numerical value of the pattern has to be pre-computed, and the numerical value of the leftmost substring in the text has to be pre-computed. These are the three things we need to pre-compute. So um, so I'm just going to state here that we have a temporary value which is d to the power m minus 1 mod q. If you're using systems like Python, you can, where you can go up to larger integers. You don't even need to do a mod q, but let's say if you want to do a mod q, you could just pick the value that is typically used in your dynamic programming or recursion solutions. It's large enough, and anyway, there's no danger of overflow in those languages. So you can work with a value that's so large. So I'm assuming that this is something you can calculate in the form of a loop. You can actually compute x to the power m in log m time. You don't need to use order m time. But I'm not emphasizing on that here because improving that from order m to order log m is not going to change the overall complexity, because the other parts of the algorithm will continue to take order m time. Right? So let's say via a loop you can compute this. So I mean, if you want me to write this, it's just going to be, the loop will look something like this. For, or you can say repeat m minus 1 times, repeat m minus 1 times the following. I take the temporary value, I multiply it with d, and I take a mod q. Okay, so this white whatever is in this white box is essentially expanded into this yellow box. So that's pre-computing that. Now we also need to pre-compute the values of the pattern and the value of the leftmost substring in the text. So let's call the value of the pattern as p value. It's initially 0, and then we go through each character of the pattern, right, from left to right. So our pattern, remember, has a length of m. These are all characters. So for I varying in the range from 0 through m minus 1, we're going to take the ith character of the pattern and we're going to incorporate it into the growing p value. So that means we will take the existing p value, right? Again, we are following Horner's rule here. So whatever value we had computed so far, if we have to add one more digit, we take the old value and we multiply it with 10 or whatever the base is. So we can say p value times the base, which is d, plus whatever the new digit is in the current character. So that is going to be p of I. Now p of I, strictly speaking, is a character. It's not a digit. So what we will need to do is to convert it into a digit. So if we are talking about a base 26 system, we would need to convert P of I to its ASCII value, and then maybe subtract the ASCII value of little a from it to get a value in the range from 0 to 25. So this will actually have to be whatever, this is going to be language dependent. Whatever the ASCII value is for your character minus the ASCII value for lowercase a. So if it's lowercase a itself, it's going to be 0. If it's lowercase b, it's going to be 1, and so on. Since ASCII values are increasing order, consecutive range from small a to small z. So we'll do that, and so that's going to be our new p value. Since we are working in the mod q system, we'll keep taking a mod q after every operation. Now we could do the same thing with the text, namely the leftmost substring of length m in the text. So the leftmost substring of length m can also be calculated in this way. Text of I mod q. And again, this is similar to, here this we'll need to convert it into a numerical value, numerical digit value. So this is the, so at this point pre-processing is done. Pre-processing is over. Now we move to the matching phase. So how do we do the matching? We have this fixed length. So actually let's go back to the brute force. What we had in the brute force was simple loop like this. For shift in the range from 0 to n minus m, all that we are doing now is doing this equality, right? So so that's what we're going to do. For shift in the range from 0 to n minus m, in the range from 0 to n minus m, if the p-value is equal to the t-value, then we know it's a match. Okay, so we could directly append something to the answer if we are not interested in matching collisions. Otherwise, if you want to be safe, you could verify that all the characters from 0 to m minus 1 in P are going to match all the characters from index shift to shift plus m minus 1 in T. And append shift to result if so. Okay, otherwise you can just append. If you picked a value of q that's large enough, the probability of collision is less. You can directly append as well. Now, the p-value remains the same, of course, but the t-value has to be updated. So every time, well, actually, irrespective of whether or not there is a match, the next t-value will have to be obtained from the previous t-value by applying the same formula. So the new t-value is going to be obtained from the older t-value by taking the older t value and subtracting out what we had computed here, which is stored in the temporary variable, temp times the leftmost digit, temp times, hold on, did we do a mod q there? Yes, we did already. Okay, temp times the leftmost digit. The leftmost digit is uh, t of shift, right? So we take this, multiply it with d using Horner's rule, and then we add to that the rightmost digit, which is coming into the new window. So the old window was from shift to shift plus m minus 1. The next window is going to be from shift plus 1 to shift plus m. So the rightmost digit in the new window is going to be shift plus m at index shift plus m. So that's what we need to add, t of shift plus m. And again, when I say t of shift plus m, for both of these, convert them from ASCII. Convert them to the numerical value, right? Convert to numerical values by taking their ASCII code and subtracting the ASCII code for riddle A. So it's really going to be this formula actually. Wherever there is t of shift, it's going to be the ASCII value of t of shift minus the ASCII value of riddle A. And likewise for the other. And this whole thing needs to be surrounded by a mod q. So when this is done, so the first time this is done, shift is 0. So, and then we move to shift 1. The last time this will be done is when shift is n minus m. When shift is n minus m, we don't want the window to keep getting slided. So this last line will do only when, as long as we are not at the rightmost edge. Okay, and then we can return the result. Jojan?
So can you hear me?
Yeah.
Probably you might have covered. So the one followed by zeros, the value of q, is that the highest prime number that can fit in the integer width, the 32-bit integer?
It's not highest, but it's easy to remember. It's
But
yeah, this is 30, assuming 32-bit. But as I said, it's not just q, but also q times 10, q times 26 that
so
needs to fit.
you can take any arbitrary prime number, right?
Yeah.
However, the highest means the less chance of collision. Am I right?
Yeah. Yeah.
Okay, and that has no correlation with D being 26 because I was confused by the line you draw from
okay.
to Q.
No correlation with.
Oh, okay.
So I should.
Oh, okay, and I have a maybe so instead of doing this multiplication, you are always trying to get rid of the most significant digit, right? For example, you got 415. You want to get rid of the 4, right? You can always do that with an AND operation of FF and then a nibble, for size of a nibble, 4-byte shift, right? Can you do that?
Well, these are not necessarily bit aligned, right? Because these are arbitrary bases. Since these are arbitrary bases, base d, if you want to subtract d to the power m minus 1 times that leftmost digit, I'm not sure if how you would do that for an arbitrary base using bitwise.
Oh, okay. No, I was just since it is getting rid of the most significant bit, I just came to my mind. I was thinking, I was just throwing some. It will work. So I was just throwing
Yeah,
that.
if it was base 2, then we could have done that.
A
But
base.
since it's
Okay.
base d in general,
Oh, okay. Okay. Thank you. Can I lower my hand?
okay. So that's Rabin Karp, expected to run in linear time with a large queue, and particularly if you don't do any verification, even if the matches are long or many in number, it would still run in linear time. But there's always a possibility that you could get a bad input and which might force your algorithm to take more. So we want something that runs in linear time in the worst case. Arif?
Hi, Omkar. I am wondering why we are multiplying by d and not 10, because we are assuming that we are using integers, right? And
We are assuming lowercase letters here. We're assuming lowercase letters here as you will be given in this problem also. Here you're
right, but we
given
are converting it into numbers, right?
numbers, yes, but base 26 numbers, not base 10.
Okay.
So that's why D is 26 there.
Oh, so we are assuming all lowercase letters. That's why 26.
Yeah, since it's given that they are only lowercase English characters, both the text and the pattern. Gaurav?
Hi, Omkar.
Yeah, hi.
Omkar, what is the semantic role of temp in that algorithm?
The semantic role is just to avoid computing it over and over since it's used over and over in every step. It's just, what do I, it's just the power of the base that is associated with the place value, right? The, for the leftmost digit in the old window. So it's just the power of it's just the place value of that leftmost digit. So it's a value that we just pre-compute and then,
Yeah, and while adding, we don't seem to be doing a multiplication, but while subtracting, we are doing a subtract with that place temp.
yeah, because when adding, whatever digit we add becomes the least significant digit. Whatever goes from the left side of the window is the most significant digit. So the place value for associated with this incoming digit is a 1.
Okay,
Place value associated with this outgoing digit is d to the power m minus 1.
okay, I got it. Thank you.
Uh, Okay, so this was the first method that I wanted to cover. Um, you can look at it as a transform and conquer strategy, where you look at the substrings being compared as integers, and then you just unpack what all you need to get those integer values and use optimizations like fixed length sliding window, this fixed length sliding window approach, and add a mod queue to handle overflow um, with a large queue, and that would make this run.